name is Nancy Bush, and I'm the Dean of the Graduate School of Arts and Sciences here at Fordham. I'm also a yearning faculty member in the Department of Psychology. I don't get to spend as much time on research pursuits and with students as I'd like to. But activities like this remind me of where my heart is. So I was very pleased when David asked me to do an introduction tonight. I'm very pleased to welcome you to what will be the first of the annual Anastasi lectures. The Anastasi lecture continues the profound and lasting legacy of Ann Anastasi in the study of psychology at Fordham and in the field overall. For those of you who don't know about Ann, she was homeschooled as a child, admitted to Barnard College at the age of 15. She received her doctorate from Columbia University, then taught at Barnard and Queens College before she came to Fordham. In 1972, Anastasi served as the president of the American Psychological Association, the first woman in that office in 50 years. Her text, Psychological Testing, is considered by many to be the definitive text in the field. Ann Anastasi was a longtime Fordham faculty member and chair of the Department of Psychology. She retired from full-time teaching in the department a few years before I arrived at Fordham, but she was still an active writer for the 20 years after her retirement. I had the privilege of getting to know her in those 2 decades, eventually becoming the first female chair after her. And you talk about big shoes to fill. I still don't think I filled them. And then I had the joy of inhabiting her physical office when I stepped down as chair. At that point, a lot of her papers and her books were still in that office. They gave me access to those books, some older ones that I hadn't looked at before, and I appreciated being able to read and see some of her notes about. I also very much appreciated looking at some of the memos that she wrote in her capacity as chair. Now, having spent the last 10 years of my life connecting with alums as dean of the grad school, I have heard lots of tales from her former graduate students that tell tales of the anxiety she created as she shaped their approach to scholarship. As we all know, nothing less than excellence was acceptable to Ann. But her approach to quality certainly provided a role model for me in a different way. She expended a great deal of effort in recognizing excellence wherever she found it. I treasured the carbon copies of letters she wrote to others, acknowledging the hard work of library staff in locating resources for her latest book. The kind of unsung heroes of the university were not lost on Ann. She acknowledged them all. And in these days of multiple drafts, I still aspire to her practice of submitting papers so polished that an editor would never think of giving her the ubiquitous decision of revise and resubmit. Indeed, one editor that did dare to give her such a decision received a very polite note that she was withdrawing the paper from submission to his journal, and the paper was subsequently published elsewhere without any revision. Her research and scholarship established her as one of the preeminent psychologists and academic scholars of her era. Ann's achievements were recognized by numerous awards: the Distinguished Scientific Award for Applications of Psychology from APA, the Educational Testing Services Award for Distinguished Service to Measurement, the American Psychological Foundation's Gold Medal for Life Achievement, the American Educational Research Association's Award for Distinguished Contributions to Research and Education, to name a few. My favorite story, though, is that in 1987, Dr. Anastasi responded to a call from the White House about an award. She quipped with a comment that she thought she'd received them all. And the response was, "There was still one more to come. We missed you." she was presented with the National Medal of Science, one of few women to receive that award. I am really pleased that the psychology department and the Anastasi professor in psychometrics and quantitative psychology, Dr. David Rajewsko, is continuing Anne's tradition of service to the university by beginning this lecture series. I believe it's a fitting tribute to her scholarship and her intellectual leadership. And now I'd like to introduce the chair of the department, Dr. Kathy Shue.
I guarantee you I will be filling no big footsteps here. I'm just a regular old chair. I'm here to welcome you all as chair of the department. We have many of our faculty here. Last year, which was my first year, we celebrated the history of psychology in New York and the history of psychology in the department, and so we began talking in a more formal way about many of these kinds of things. At the same time, we were tremendously fortunate, and we are honored to have been able to have David Rajewsko come and join us as the endowed Anastasi chair. We were thrilled by that, and we celebrated that around this time last year. In the same vein, we were very happy to hear that David was interested in continuing this as an annual event because Anne is important to us, the department is important to us, the psychometrics program is important to us. So I thank you all for braving the insanity going on out there and actually getting here, and I look forward to hearing you talk.
It is my pleasant duty to introduce Frank, but before I do that, I want to say a few words acknowledging and thanking all the people who helped organize the event by providing funding and are helping organize it. And I want to thank the Dean of Faculty of Arts and Science, the Dean of the Graduate School and all the staff in her office, the psychology department and everyone in the office, and the various graduate students who volunteer to help in many capacities. And in a self-congratulatory note, the Anastasi chair. And that said, I want to say a few words about Frank, our speaker today. When I decided to start these lectures, I saw that what we want to do is to have an annual event where we invite leading scholars in the field of measurement, methodology, testing, who can talk about issues which are of interest to both professional researchers as well as to an intelligent, wide audience, and to communicate what is new in research in our field and which direction the field of measurement methodology in psychology is going. And we were very fortunate that when I called Frank, he was able and willing to come. He only insisted on very tight security, but I think we delivered. And so I want to tell you a few words about Frank's career. Frank received his PhD in industrial and organizational psychology from Purdue. And during his career, he's held position at the U.S. Office of Personnel Management Research at George Washington University and at Michigan State University. But for the last 24 years, he has been a professor in the business school at the University of Iowa. He has been, throughout his career, working on many topics, but I think the one that I find central and you can see it from the beginning, are issues related to personnel testing, selection and placement, and the role of intelligence and personality in job performance, and issues of validity and generalization of validity of these tests. This work in the area of I/O psychology has also motivated him to move into this area of developing meta-analysis. And as most of you know, his work with his now deceased collaborator, John Hunter, on meta-analysis is very widely cited, very widely used. He has second edition or third edition of the book? Second edition out. Numerous papers, and he's one of those rare scholars that has made very major contributions to both to the methodology and to substantive areas. And he was recognized for these papers, again, receiving many prizes. I just mention a few. The APS Cattell Award for Applied Psychology, the APA Distinguished Scientific Contribution Award, the SIOP, which is the Society of Industrial and Organizational Psychology, Distinguished Scientific Contributions, and many others. And probably for the academics among you, the most impressive statistic is that among 2,500 management scholars, he is at the 99th percentiles in terms of citation rate. So, that's all I have to say, so I'm very happy to welcome Frank.
Well, thank you, David. Nice introduction. I've done other memorial lectures, for example, one for Bob Wary at Ohio State, but this one is really special for me because Anastasi was one of the very first big names in psychology to support the work that Jack Hunter and I did in meta-analysis and validity generalization. Starting right after 1977, when we first developed this method, she incorporated this in the successive editions of her psychological testing book, which had a major impact. And just before I came, I went back and relocated a series of exchanges, correspondence between Ann and myself, sent that to, ranging from 1976 to 1979 on these issues. What she says, here's how I'm going to introduce this into my next edition of my book. Here's what I'm going to say, and so forth. And, Kathy has said that they want to put those letters in the archives. Apparently, have a big set of archives. She's a remarkable woman. I didn't know her personally. I would run into her at APA conventions. She seemed to always be there, and always, willing to sit down and have an extended conversation on any subject related to psychological testing, psychology in general. They're a very delightful, intellectually stimulating moment. In addition to the slides of mine that you have there in your handout, there is a set of references, and these are my insurance in that as I proceed through this talk, many of you may wonder whether I'm telling the truth. And so that's what the references are for. And I'll refer to them by number, and if you're skeptical, you can read those and see the basis for what I'm saying. Well, by way of introduction, let me say this. I once published an article entitled, "What Do Data Really Mean?" And this was an appropriate title for me because since I finished my dissertation in 1890, I have been concerned with that. I've been concerned with that question. How do we know what data really mean? What are the hidden meanings of data that our usual approach to interpreting data don't get, and therefore mislead us? And I've got quite a few publications in this vein. I'm not going to go over here. Let me say that this interest is what led me to work with my late colleague Jack Hunter, that you mentioned, to develop meta-analysis methods. These methods were aimed at determining the real meaning of research labels, which are usually very conflicting. A lot of different conflicts. Different studies got different results. Difficult to make sense out of the literature. And over the years, these methods have been tested and used and presented in many journal articles and 3 different books. Our original book, and then our first edition of the current book, the second edition. And number 1 on your list is the 2004 current meta-analysis book. Over the years, these methods have been applied to many different literatures, and almost always the interpretation is that resulted was that the research findings were not nearly as conflicting as they appeared to be. They were much more consistent than they appeared to be. And it became apparent to me that the way in which we interpret data using significance tests allows data to simply lie to researchers and create false conclusions. I'm going to give examples of this. But in doing this, I became convinced that there was a strong cult of naive empiricism in psychology and the social sciences, which consisted of the belief that data is a direct source of truth in research. In fact, when I was in graduate school, long after that, I would repeatedly hear people saying, "Don't give me your opinion. Just let the data speak. Look at the data, see what the data say." Well, if you do that, I'm going to be contending and giving you some examples of this. If you let the data just speak for themselves, they will typically just lie to you. And that causes a lot of problems in the development of human science and psychology and the social sciences. Goal in psychology and all the other social sciences, all sciences in general, is to develop theories that constitute knowledge. Theories are explanations. You want to develop theories or explanations of how things work, why they do, what the causal relations are. In order to do that, you have to have accurate estimates of the relationships among variables and constants. And the way in which we interpret these relationships retards the development of, retards the effort to get accurate estimates of these relationships. These are the building blocks of theory. You've got to know how things relate to each other. Once you do, then you can say, well, let me propose a theory that explains these relationships. But you've got to be able to nail the relationships down to begin with. And so I'd like to present now to you an example of this problem. This slide shows 16 studies done in 16 different organizations relating a test of decision-making ability to performance on the job. And there's a wide range of sample sizes and a wide range of correlations. Half of them are statistically significant, half of them aren't. Now, the next slide shows Lisa data in a way that makes it easier for you to see how much variability there is. The largest correlation is 15 times larger than the smallest. Tremendous amount of variability here in these results. This is what the graph would look like if instead of 16 studies, we had 16,000 studies. It would be approximately like this. Maybe not perfectly, not approximately like that. And tremendous variability, minus 104 to 104 in the correlations. Now, let's go back to this slide. Take a little more look, closer look at it. The correlations range from 0.02 to 0.30. That's a ratio of 15 to 1. The largest one's 15 times larger than the small one, than the smallest one. Now, if we just take these data at face value, what would you conclude? You would conclude that the relationship varies all over the place, but it's always positive. There's always a positive relationship. But that's not the way data is commonly interpreted. It's commonly interpreted using significance tests. And if you look at the Anastasi there, you'll see that 8 of the 16, half of them are statistically significant, half are not statistically significant. And all too often in the past, that was interpreted, finding like that was interpreted in one or two different ways. The first way is that there are two different kinds of organizations here. There's a set of organizations in which this test works. There's a relationship. And there's another set, also 8 organizations, in which there's no relationship. It's not significant, it's equal. That's a common interpretation. It's not statistically significant, it's probably just due to chance, the real value is equal. So that's the moderator interpretation. There's two different kinds of organizations. There's also a tradition of the majority vote interpretation, which says that you can conclude there's a relationship if the majority of studies get a significant relationship. Well, here we don't have a majority. We have 50-50. Since you don't have a majority, your conclusion would be there is no relationship here between any of these, between decision-making tasks and requirements in the organization. Later on, we'll see that the naive interpretation, which doesn't use any significance test, is less erroneous. It's not perfectly correct, but it's less erroneous than either interpretation based on using statistical significance tests. Now, let's go to 4. This is the same, but this is what this distribution looks like when you correct for sampling. 98% of all the variability that we saw in the first 3 slides is all sampling error. And the square root of 0.98 is 0.99. That's the correlation between the observed value of the correlation and its sampling. This shows, now how do we correct for sampling error? We have formulas that tell us how much sampling error to expect, and you compute that. That's the sampling, expected sampling error variance. You subtract that from the observed variance, and that's the correct sampling error. That's explained in the meta-analysis book. Well, how many researchers would ever have the thought cross their mind that there's a very, very high correlation between the data they see and the sampling errors underlying the data? Now suppose you only explain 98% of the variation from sampling. Suppose we only explain 70%. The correlation between the square root of 0.70 is 0.84, so you still have a correlation 0.84 between the data you see, your observed values, and the sampling errors. Every value is an underlying value, population value plus a sampling errors. This shows just how they dominate the data and illustrates the fact that virtually all researchers underestimate what a huge, huge impact sampling error has on the data that they observe. Now let's take a look at measurement error. Every one of the correlations we saw in slide 1 are downwardly biased by measurement error of both variables. And we can correct for that downward bias. The reliability of this particular test was 0.80, and the reliability, inter-rater reliability of the ratings of job performance, we're going to use this to measure job performance, is 0.50. So we can use those to correct by using the standard, applying the standard correction for information. And we do that, and this is what we get. All the correlations are larger. They've been increased as a result of, they're no longer biased downward by measurement error. However, statistical significance does not change. The correlation goes up when you correct for measurement error, but so does the standard error. So the statistical significance level does not change. So we still have maximum conflicts here. 50% of them are not significant, 50% of them are significant. This slide shows a histogram of the data corrected for measurement error only, and shows you just how much variability there is. And we now have a ratio of 20 to 1. That is, the largest correlation is 20 times larger than the smallest correlation. Now, why would we want to correct for measurement error? It's well known and well accepted that when we do research, we're interested in relationships between constructs, not the relationships between measurements. So we want to eliminate the effect for theoretical research, which we're trying to estimate relationships among underlying constructs. We want to eliminate the bias of these measurements. So that's the reason for it. This slide shows what the approximate distribution of correlation would be correcting for measurement error if we had an extremely large number of studies, not 16, but 1,600.
Dr. Schmidt, I'm very sorry. Could you talk into the microphone, please? It's very hard to hear you.
You can't hear me?
No, much better. Thanks.
Really?
Yes.
Okay. I thought I was pretty much allowed now. I'll try to stay closer to the mic. The mean is 0.32, and there's a huge amount of variation. The standard deviation, indexes of variation, is about over 1/3 as large as the mean. So if we give very large numbers of studies, corrected for the biasing effects of measurement error, we would see even larger differences among the different studies. Now, let's now correct for sampling. We correct for sampling after we get this distribution. The mean is 0.32, and the standard deviation is pretty close to 0, 0.01, and the variance is 0.001. This is what we would call a full meta-analysis, or those data sets that are affected only by sampling error measurement. Every scale has measurement error. No such thing as a perfectly reliable scale with no measurement error. Not just in psychology and social sciences, but in the physical sciences. There's always measurement error. And there's always sampling error. Some people say, well, we don't have sampling error, we have a whole population. That's really not true. That's really pretty hypothetical. All data has sampling error and it has measurement error. There are other artifacts I'm going to talk about later that affect some sets of data. But these are the two that affect all data sets. And one reason I think the meta-analysis has been successful and just accepted is that it deals simultaneously with measurement error and sampling error. We look at what the statisticians do. They tend to focus on sampling error and ignore measurement error because statistics didn't really invent the concept of measurement error. It came from psychometrics. What do the psychometricians do? They say, let's pretend we have an extremely large sample size. So we don't have to worry about sampling error, we'll just look at measurement. But with meta-analysis, you take into account both simultaneously, and you have to do that in order to prevent the data from lying to you in one way or another. So note that this interpretation is not only more accurate, but it's also more parsimonious. The basic conclusion is that we're pretty close to having only a single relationship, 0.32. There's not very much variation around it. Now consider the earlier interpretation. The first one was that there are two different types of organizations. Those in which this thing works, and those in which it doesn't work. The moderator, you can see that's not true. Another interpretation was that there is no relationship because we didn't have a majority that were significant. We only had 50%. Well, you can see that's not true. Now let's recall the naive interpretation in which you just take the data at face value and you don't use any significance. That interpretation was the relationship is always positive, but it varies quite a bit. Well, the second part of that isn't true, but the first part is. So it's half true, whereas the interpretations based on statistical significance testing are completely false. They're not even half true. So the naive interpretation is actually less wrong. So this example illustrates how data can and do lie to people. They use standard methods that are widespread in terms of analyzing and interpreting data. Now I want to talk about some other examples in a little less detail. A former student of mine, Denise Ohms, is in the psychology department at the University of Minnesota. She studies expatriates. She's originally from Turkey. She's very interested in the performance of expatriate management. You know, we have a lot of multinational companies. They send managers to Singapore and China and Europe, and she was interested in the hypotheses that different personality traits are important for success in different cultures. And she did a study involving quite a number of different cultures, and she found that she used the big 5 personality traits, conscientiousness, extroversion, agreeableness, and so forth. And she found that any given personality trait was significantly related to performance in some countries, but not in others. And it looked like, on the surface there, that this was a finding that would be very useful to multinational companies. Because when they decide what manager to send to what country, they would want to send one that is high on the personality trait to contribute to success in that culture. But then she did an analysis just like the one that we talked about. And almost all of the variability across countries was sampled. Again, you have a picture of apparent complexity, which people can usually make sense of. They say, oh yeah, that country's so-and-so. Yeah, that's what you would expect. But the extroversion would be important like that. Ex post facto explanation. But virtually all the variance was due to sampling error, and the same correlations pretty much was, all countries had the same correlation. While it might have been disappointing, or maybe HR managers in multinational companies, note that this findings again. It's much simpler, it's more parsimonious. It's another example of what we should be doing in science, looking for the simple laws and relationships that underlie the apparent complexity we see at the surface structure, deep structure level. There's a very good chance that the structure will be much simpler, and that occurred here in this case. Here's another example. One of my PhD students recently completed his degree. He's now a professor at a Canadian university. He's from Korea, in Suwon is his name. And he had the hypothesis that there are great cultural differences between East Asian countries, and these cultural differences are much greater than they are among between different European countries. And he studied Korea, China, Japan, Taiwan, and Singapore. And in each one of these countries, this was quite a job, but he found all the studies that have been done relating to personality traits to performance in those countries. And in each country, he did a meta-analysis. So you don't just have a single correlation, you have the average, essentially, in each country. And it really did look like that there were important country differences at the level of the mean correlation. But he knew there was such a thing as second-order sampling error. What does that mean? Well, when you do a meta-analysis like this, you average out most of the sampling. But you don't average it all out, because you don't have an infinite number of studies. So there's still some sampling error left in the meta-analysis means. That's called second-order sampling error. And there's a way to calculate what that is. And when he did the second-order meta-analysis, he found that, again, almost all of the variation in these mean values across different Asian countries was due to sampling error. The average across the personality trait was 86% of the variability due to sampling error. And for 2 of the 5 traits, it was 100%. So, even though it's very plausible that different personality traits are important in Vietnam and in Korea, it didn't really pan out at the deep structure level. And that's important. Now I want to give you another example. It's not even from psychology. It's from traffic safety engineering. And I found out about this from a correspondent with a guy named Power, who, in his article I'm going to describe is number 15 on your list of references. Power has campaigned against the way in which use of significance tests distorts data interpretation of traffic safety data for years and years. And he tackled this with a meta-analysis-like procedure. Quite a large number of studies had been done on the effects of having a shoulder, highway shoulder. Shoulder is an area where a car can pull off if it has car trouble or have stopped for any other reason in a paved area. And a lot of studies have been done in different states comparing accident and death rates for highways that have shoulders and don't have shoulders. And guess what? None of the differences were statistically significant. Every one was in the same direction. There are always more accidents and more deaths when you don't have shoulders. But because they were not significant, and because the traffic safety people followed the rule that it's not significant, zero, the conclusion was there is no effect. And when he did the meta-analysis, he showed there's clearly an effect. More people, but this is, I like this example because it's a case in which people died because of reliance on significance. Because the data is interpreted using significance tests, people lost their lives. There are also a lot more accidents that didn't kill people. And he did the same kind of analysis for the increases in interstate speed limits. In 1986, in 86 and 95, interstate speed limits were increased. And they were increased on the basis of studies that showed no significant increase in deaths or accidents. But all the studies showed there were, just took it at a naive face value, there always were increases in deaths and accidents, but they didn't reach statistical significance. And in the meta-analysis, you can see very clear pattern, just like this. As I say, I like that example because it's more hard-hitting, I think, than just saying, well, if you rely on significance tests, you'll misinterpret your data. In this case, it caused people to die. In this particular example, the reliabilities, the same measure was always used for performance and for measuring decision-making ability, so the reliabilities are the same. But in real data, they aren't the same. So differences between studies and reliabilities break additional variation in observed values. And the method of correcting for measurement error in the software that we developed, that's number that is, but Beeley and I developed a Windows-based meta-analysis procedure, and it makes will correct for variation, not just do sampling error, but do variations in measurement and other aspects of some of you may be tempted to say, well, this data is all correlation. And I don't do correlational research, I'm an experimentalist, I do experiments and so forth. Well, if you do experiments, the relevant statistic is not correlation, it's the d-value, the standardized difference between the experimental group and the control group. Or it could be between two groups such as men and women. The d-value statistic has even more sampling than the correlation group. Furthermore, most experiments have lower sample sizes, so they have more sampling error. That is. Well, we have a behavioral lab in my business, and it's very common for people to do experiments where they have 20 people in the control group and 20 people in the experimental group for a total of 40. Most correlational data has larger sample sizes. So they have tremendous sampling. So the same principles apply to experiments as apply to correlation. And in an earlier article, I presented results from the experimental nature to illustrate these same principles. I use detail. Okay, the nature of this talk and time constraints here totally prevent me from talking about how you make corrections for sampling error once you correct for measurement error and so on. And all of that is covered in the meta-analysis books that I cited, in particular. I recommend the most recent one, the 2004 one. These methods that Hunter and I developed are the only meta-analysis methods that take into account both measurement error and sampling. The other commonly used meta-analysis method is that Hedges and Holden. It doesn't take into account measurement. However, it's really interesting that Larry Hedges says that measurement error is important and should be taken into account, but his method doesn't do it. In the most recent issue just came out, edition of the Handbook of Research Synthesis, he states in one of his chapters that measurement error is important and should take into account for this method does not do that, and I'll document that in the analysis later in this talk of meta-analyses appearing in Psychology, which is the premier research, review journal in psychology. Now I'd like to talk about the implications of this kind of an approach for construct proliferation. Big problem in social science. People try to make their reputation by discovering a new construct that in the last 20, 30 years, social science has overlooked. New important construct. Like Global and Tyler said, yeah, so there's a lot of research on job satisfaction. We have a new construct called job involvement. Well, how different is job involvement from job satisfaction? As time goes by, our whole field, at the surface structure level anyway, becomes more and more complex because more and more people are inventing more and more constructs. This is not good from the point of view of parsimony, or from the point of view of the obligation I think we have to look for the deep structure relationships that are very good chance to be less complicated than a surface structure relationships. For two constructs to be distinct, there are two things that have to happen. First, there has to be an articulation of the conceptual difference. And that's an easy thing to do. It's easy for Lola and Tyner to say, yeah, here's what job satisfaction is, here's what job involvement is. And they're not the same. Conceptually, they're not the same. Same thing for organizational commitment and job satisfaction. Job satisfaction measures how much do you like your job, really. How satisfied are you with your job, whereas organizational commitment is supposed to measure your opinion of the organization, whole organization you work for. Do you value it? Do you have a positive attitude? In a recent publication, which is number 4 on your list of references, we did a meta-analysis making appropriate corrections for all the different varieties of measurement here. And we found an average correlation, actually a correlation with very 0.92 between measures of organizational commitment and measures of job satisfaction. And what this suggests is that while these are conceptually distinct in the minds of the theorists, this distinction isn't being made by the respondents in the real world who are being given these surveys. They're not making the distinction. So it's not, that's the second requirement. First requirement is being conceptually distinct. That's easy to meet. The second requirement is that they have to be empirically distinct so that people do make the distinction, which they don't seem to do, are organizational commitment and job satisfaction. I gave a talk earlier today, and in that talk I presented research that shows that even if two constructs are identical, that the measures of those constructs will not correlate one even after you correct the measurement because of shape difference, true score versus constant. And what the overall conclusion from that study was that if you get a correlation anywhere between 0.90 and 0.96, after you fully corrected for measurement, then that suggests they're really the same thing. So they're not just correlated but distinct. Typically what happens in the literature is that people will correlate their construct with another construct. Let's say job involvement, job satisfaction, or organizational commitment, job satisfaction. And they'll get a correlation of 55 or 60, and then they correct it for measurement error using coefficient alpha, which doesn't fully correct the measurement error, and they get about 0.70 or so, and then they say, well, yeah, they're correlated. I mean, these constructs are correlated, but they're still distinct. They're not perfectly related. In fact, they may well be. In the example I gave, the most erroneous interpretation, the two most erroneous interpretations were those using statistical significance. And there's a number of articles that have been published, some by myself and some by others, and numbers 7 and 9 are examples of this on the reference list, showing that people are really, researchers tend to be basically addicted to significance. And they have this addiction because they have false beliefs about the meaning of statistical significance. And I'd like to just run over some of these. The first one is, if you have a significant finding, that means it's reliable. A statistically significant finding is a reliable finding. How is that? What does that mean? It means it will replicate. Suppose it's significant at 0.05 level. Many people interpret that as meaning that if I were to do a replication study, I'd have a 95% chance of replicating the result. When in fact, the probability of replicating the result is usually about 50%. Why is it 50%? Because the average statistical power in most literatures, it averages about 1.50. It's just simply not true. That a significant finding is reliable. One that you're all aware of is the belief that still exists today, that the p-value is an index of how important the relationship is. P-value is mostly a function of sample size. Very low p-value means you have a very large sample size, or else you have a really giant effect if we don't have a giant. Another belief is, this is the worst one of all. If it's not statistically significant, it's probably just due to chance that the real relationship is zero. Well, in fact, if it's not statistically significant, it's usually due to low statistical power. Lipsy and Wilson in the 90s published a review of 302 meta-analyses in American Psychology. Only 2 out of the 302 had a zero effect. What that tells you is that the null hypothesis is almost never true. So if it's not significant, it's almost certain that's because your power is low, and it's not because there's no relationship. And these meta-analyses they looked at were those for the effectiveness of various psychological interventions. There was only one that had zero effect, and that was the open classroom. And there were 2 meta-analyses on the open classroom. All the others, those various therapies and so forth, had an effect in the appropriate direction. Another one is this, false belief. You cannot have a science unless you test hypotheses. Therefore, we have to have significance tests because you have to have them to test hypotheses. Well, that amounts to the proposition that physics and chemistry are not scientific because they don't use significance. They use point estimates and confidence intervals. And in fact, if you talk to physicists and chemists, many of them will say the use of significance testing is a sign of a pseudoscience. It's not really, it's not only is it not required, it's a sign of a pseudoscience. Another argument is this: science has to be objective. You can't have a subjective science. You've got to have objective standards of scientific science. And the statistical significance test is objective. Any two people applying it are going to get the same result unless they make a mistake. So that's an objective measure of scientific evidence. Well, the problem is, that implies that the physical sciences are not objective because they don't use significance testing. They use point estimates and confidence intervals. And they're just as objective. There's no way that you can say significance testing is more objective than point estimates and confidence. Finally, there's the argument that's made a lot that the problem is not the use of significance tests, it's the misinterpretation and the misuse. I don't have time to go into the details on that. You can check reference number 9 addresses this. Even when significance tests are not misinterpreted. They're interpreted the way Fisher and Pearson wanted to interpret it. They still regard the development of human knowledge in comparison to what you get when you use point estimates. Now, there's been some improvement in this area, some to address this problem and improve the situation. Many of you are aware that there was an APA task force on significance testing and psychological research that published a report in 1999 in the American Psychologist and Wilkinson Report. And it said that researchers should report effect size estimates and confidence and analyze their data that way. As a result of that report, the 5th edition of the APA publication manual and the 6th edition, 5th edition came out in 2001, 6th edition in 2009, they both say researchers should quote almost all report point estimates and confidence. Now, and also right now, I checked this with Bruce Thompson, maybe more now, but there are 24 research journals that require you to present point estimates and confidence. And the number is maybe larger by now. So there's been some movement, but if you, all you have to do is open a lot of mini psych journals, and you will see that we still have a long way to go in this respect, in this data analysis. One major difference between using confidence intervals and significance tests is that with confidence intervals, when you look across the confidence intervals in the different studies in your literature, they almost all overlap. It shows you the amount of error in each estimate. That's the confidence interval. And the confidence intervals tend to overlap. That creates the impression that, well, maybe they're all estimating the same thing, but the confidence intervals overlap. But if you use significance testing, you get the kind of thing that I showed you with half is significant, half is not. And the temptation is to say, well, half is 0 and half is not 0. Now, we've just been looking at sampling error and measurement error. Those are the only two, as I said, that are present in every study. But there are others that are present in some studies, but not others. And here are some examples of that. Data errors, typos, coding errors, errors, transcription errors, Dookie, I'm a statistician, and others have done studies of large data sets. These people that they hired to help in the analysis of large data sets, they've always run error checks. And they report that they always found substantial numbers of data errors in any database. Now, if you see a correlation of 2.6, you know that's data. But if you see a correlation of 0.35 and it really should be 0.53, there's no way you can tell that's okay. Barring going back to the original researcher and looking at the data and trying to see if you can trace down an error, there's no way you can detect any of these data. These data errors produce additional variation beyond sampling error and measurement error variability. And often, you just can't find the errors. Then there's range restriction. The lower the variability of a variable, the lower the correlation is expected to be with the other variable. And there are basically two types of range restriction. One is pretty darn rare. One is correct range. That's correct range restriction. If you had an admissions test here at Fordham, and everyone who was above the cutoff was admitted, and everyone below was not, and that's the only thing you use. You didn't use anything else. That would be direct range restriction. That's very, very rare. Instead, what you will do, I'm sure, is you take into account other things, undergraduate grade, a whole lot of things. So in effect, the range restriction on the test score is going to turn out to be essentially indirect. Because you're hiring on a basis of deposit. Recently, another example of indirect rank restriction is people who sign up for your psychological experiment. They self-select on various credits. That's an example of indirect. There's no direct cut on any measure, but there's indirect selection, self-selection. Recently, we developed our colleagues and I developed a method of correcting for indirect rank restriction that can be applied to pretty much all data sets. All you need to know is the two standard deviations of restriction. You don't need to know all the usually unavailable information that is required to use the Thorndike and Wellington indirect range restriction practice. That's why it's partly been used. You usually don't have all that information on the variable, on all three variables. And we did a, let's see, this is, I'm going to give you the, this is number 2. We also did, number 3 also shows that shows the demonstration that this new method is active. This is the simulations that I published in so we developed this method and tried to correct indirect restriction, and we showed that it's accurate in simulation studies that were published. And what are some of the, I'm not going to talk technically about this method not working, but I'm just going to give you some of the implications. The average estimate in many different meta-analyses pretty much came out the same. That the correlation between general intelligence and job performance for the middle range of jobs, meaning selected jobs, about 0.50. When we reanalyzed all that data with the new method, correcting for indirect range restriction, because what is indirect range restriction? The average is about 0.66. That's about 30% increase. So these are, it's not a technical fine point. It really makes a difference in your estimates. We also use these new methods to determine a more accurate ratio of the importance of mental ability to personality traits. And again, without going into a lot of detail, and the detail is in number 14 on your sheets. The new finding is that mental ability is 3 times more important than the trait of conscientiousness for job. Used to believe it was like 2 times. And it's 5 times more important than the trait of emotional stability. So these ratios have changed. Relative importance changed when we use more accurate method of pricing for range. In the past, people said, well, we know we have indirect range restriction, but we don't have the information to make that correction. We'll just use the formula for direct range restriction, and it leads to substantial underestimate. So another one is dichotomization. It's not that uncommon for researchers to dichotomize their measure into the high group and the low group, the above the median, below the median. I think that makes it easier for readers to understand. Well, that loses information. Many are Jacob Cohen and Bob McCall and many others have written very nice articles showing how that loses information and it's very, very and reduces relationships with other variables. It's pretty easy to correct for dichotomization methods. Our methods, so we have that before. And then imperfect construct with suppose you want a measure of general intelligence, but you can't get it, so you use education. You have education. Well, the correlation between the two is about 0.55, approximately that. Now, so that's what's called a proxy measure. So it's going to have construct validity problems, and the correlation between education and actual mental ability is quite a bit lower than the correlation between a good measure of mental ability and there are ways to correct for imperfect construct validity. We discussed those in our book, but boy, it's great if you have all the information you need, all the different relationships that will allow you to do that. So typically, You can't correct for all artifacts. You can correct for some, maybe most, but there are others you can't correct for. So when you wind up saying, well, we couldn't account for all the variability as being due to artifacts, there's some remaining variability, then do not jump to the conclusion that they're moderate. Because you didn't correct for all the artifacts that create variability. So you could say, we didn't, maybe if we could, we would have zero variability. We can't conclude that there's, that's what people do. And that's why I campaign against that type of automatic conclusion that there must be moderators because we couldn't account for everything is being due to artifact variables. All variants are artifacts. So, the overall conclusion here is that the injunction to just let the data speak, I think, is very naive and deceptive. The data look at you in the eye and they don't even blink and they're lying to you. This is especially true when interpretations are based on statistical standards. In individual studies, the solution would just be used point estimate calculus, not significant steps. In the integration of literature to use meta-analysis. Now, to a significant extent today, errors that are made at the study level interpreting data are canceled out at the meta-analysis level, provided that the studies that are available provide you with the information you need to enter it into meta-analysis. And so, a lot of you are aware, probably most of you, that if you look at a textbook today, the conclusions from the textbook are not based on individual studies anymore. They're based on meta-analysis. Instead of having 150 studies on something, and the author selects 7 that they like the best, give those results. They cite the meta-analysis, which incorporates all of them. And this is really the way cumulative knowledge is expressed today. So you could say, doesn't that solve the problem? Why is there a problem in the way data analysis is interpreted? Because meta-analysis is canceling it out. There's a level of research integration. Problems at the individual study level are pretty much canceled out. Well, there still is a problem, and that's because inaccurate methods, models of meta-analysis are being used. And here's I want to talk about the difference between fixed effects and random effects meta-analysis. The example I gave you, all of them really, are based on random effects models, which do not assume a priori that all the variation is due to sampling error or even other artifacts. That you test that hypothesis. Say, well, maybe that's the case, and we will test it to see. That's what a random effects model does. The fixed effects model assumes a priori that all the underlying population parameters are identical in every study, and then all the variation is due to sampling error. And that's a very highly questionable assumption in most cases. Now, we talked about Psychology earlier. That's the premier review journal in American Psychology. We did an analysis, and the majority of the studies you see today in Psychology are meta-analysis. And if you submit one that isn't a meta-analysis, if there's any possibility that data is amenable to meta-analysis, the editors will return it to you and say, do a meta-analysis, then we submit it. Now, my colleagues and I examined the meta-analyses in Psychology going back to 1978, the first one here. And this references, we published this, what I'm going to talk about now, we published in the British Journal of Mathematical and Statistical Psychology earlier this year. It's number 12 on your sheet. There were a total of 199 meta-analyses published in Psychology between 78 and 2000. 199. Of course, each one of those contained many, many methods. That many meta-analysis articles. And of the 69 that could be classified as either fixed effects or mental effects, 79% used only the fixed effects model. And there's the result. 21% you couldn't classify. Were just too bad, mostly earlier. And in fact, a lot of the early ones used the glass method. The glass method, you just can't tell. Too bad. 79% of those you classify, almost 80% were fixed effects. And we reanalyzed data from some of these fixed effects meta-analyses. We had a total of, I think it was about 6 different meta-analysis studies. It was like 58 or 68 separate meta-analyses. And we found that on the average, the confidence intervals they report, they all report 95% confidence. On the average, they were reporting 55% confidence. The confidence interval was half as large as it should be. Because the amount of sampling error that you have is what determines the width of the confidence interval, standard error. Standard error is deceptively and erroneously small in fixed effect models. So you get these very tight confidence intervals. But they didn't make correction for measurement error. 90%, no correction for measurement. So what is the upshot? You have estimates of relationships that are biased downward, but the precision is greatly overestimated. The very narrow confidence intervals, which are erroneous, they're not 95%, they're about 55% now. And so this is not just a small technical difference. This is a big difference. Overestimation of how precise the estimates are and underestimation of the magnitude of the estimate. And based on the examination we did of other psychology journals in most areas, we think psychology is pretty typical of what's going on there. The only real exception seems to be the industrial organizational literature. And here's the picture you get there from the 2 top journals. We only calculated the 2 top journals. Journal of Applied Psychology and Personality. 84% were random effects, only 16% were fixed effects, and measurement error is the reverse of that. 84% were measurement error, and 16%. This should be expanded to cover more journals. This is the point. Now, on the positive side, a very large number of studies have been done, meta-analyses have been done that use what I'm calling here a complete meta-analysis. They can pick out sampling error and measurement. And here are some examples of those. It's not just limited to industrial psychology, occupational health psychology, organizational psychology, personal psychology. You can see what some of those are. And here are some more. Differential psychology, education, and these are just some examples. There are hundreds of examples like this. So in summary, let me say this. What I've been trying to get across, and I hope I got across, is that the process of extracting the truth from data is a lot more difficult and complicated than we have assumed it is. The history of allowing data to just simply lie to us. And this is an important, we have to address this problem. You do not have successful cumulative science if you allow data to lie to you. Or if you're consistently interpreting data in ways that lead to false conclusions. I hope I've been convincing, and I take any questions you have.
education and integration mechanisms. And always find mechanisms. My question is how do we evaluate performance of the mechanisms in terms of the how do we make sure after the mechanisms not improve the performance after the mechanisms?
I'm not sure I understand the question.
Well, we have, for instance, the correction of the sampling, and then we have another one, correction of the measurement error. And then we put on paper and have the correction of both. And are we sure that the mechanism result is better than the previous result?
Well, if you question that, then you're questioning the formulas for sampling error, which have been shown to be accurate by statisticians drawing marbles from urns and so forth, years and years. They do test propositions. And you're also questioning the principles of measurement, which all that random measurement error attenuates relationship. So if you want to raise questions like that, then you have to tackle, you have to question those fundamental methodological assumptions. Not, you can't just have speculation, you got to have basis.
Sure. But, in order to do both mechanisms, in order to correct both.
Right.
In order to, if we really want to correct both, is that we will sure that correct both is that the outcome of the result will be more fair.
Right. The idea is that if you have artifactual variation and also attenuation or reduction in relationship due to processes that are understood and can be reversed through correction, then you should reverse them and make the correction.
Okay, so we'll agree that correction causes the result is more accurate. But then the next question is how much more better than
Well, quite a bit, but the answer to that is that there are simulation studies, a lot of them on the accuracy of meta-analysis method. And what the result of the meta-analysis method is compared to the known values. And the accuracy is really good. Yeah.
So what did you do? I don't label always.
Could we get the question repeated so we know what the conversation is?
All right.
Or have someone go up to the mic and ask that question, because we can't hear anything over here.
Oh, sorry. I'll repeat the question.
You made a throwaway comment early or in the middle of your talk that the unreliability or the, I think it's maybe more the sampling variability of means is greater than sampling variability of correlations. Could you elaborate on that briefly?
Well, what I said is that the sampling error variance of the p-value, which is the standardized difference between two groups, is greater than that of correlation. And to see that, you just have to look at the formula for the sampling error variance of the p-value.
Is that because the D's, for example, tend to be, for sort of in a classic two-group example, D's tend to be twice the size of
They
correlation?
do, and as long as they're not really large, they do tend to be twice the size of the correlation. That's it.
Is that the phenomenon you're talking about? So the D's tend to be large and sampling variability. Is that the,
Right.
is that just a scaling issue?
No, I wasn't trying to be that technical. I was just saying that you have p-values and they have more sampling variance than correlation. But it's due to, you can convert p-values to point by serial correlations. They will have smaller standard errors than the p-value is. And you can convert in the opposite direction.
Pretty good case being made that
with all our models, with the testing, we regard data, of course, as continuous, but that really, by right, we really should regard test data and survey data as really a best order, your argument, and the slide, I think, on the 9, you show possible distortions of the data, brought that to mind, and I'm just wondering if you had any thoughts on that point of view. We assume that our test data to be continuous, but really.
Well, the question is there a distinction to be made in how this would be presented if we were assuming our measures were only ordinal as opposed to interval, equal interval, which we typically do assume that they're equal interval. I think that if you have any basis for assuming equal interval scales, you should stay away from ordinal scales. And there is a basis for it, and that is the central limit theorem. Many central limit theorem in statistics says that if any variable is caused by a large number of small causes that are basically uncorrelated, then they will have a normal distribution. That variable will have a normal distribution. And many psychological traits in the general population fit that definition. For example, general mental ability is caused by a lot of different genes, a lot of different environmental experiences and opportunities and so forth. And so it should have a normal distribution. If you construct a scale that has a normal distribution to measure the underlying variable with a normal distribution, then the two will be linear transforms of each other, and therefore your scale will have at least an approximate equal interval scale. So that's the rationale for the assumption.
Which paper you would say that it's simulation of performance? Which paper?
Yes, which paper refers to my last answer. And it's actually the one I talked about in my earlier talk today. And it's on here somewhere. I thought just wanted to see if I can find it for you.
Number 12?
No.
$17.
Right, very last one. And that hasn't been published yet, but I can send you a copy.
I got 3.
I noticed you somewhat qualified one of your statements about correcting for unreliability. You said for theoretical work. I infer that for non-theoretical, like practical work, it may be that you believe that it's not always necessary, or maybe only to correct the dependent variable, the performance measure. Is that a correct interpretation?
Okay, the question was, are there circumstances in applied research, as opposed to research testing theories, under which you don't want to fully correct or measure error? And the answer is yes. If you're trying to determine how well a personnel selection procedure will work in predicting later job performance, you don't correct for measurement error in the test or the predictor, because you will never know the true scores. All you know is the observed scores, and so that's the correlation that indexes the value or the utility to the argument. So this whole talk is oriented to the development of cumulative knowledge and theory.
In relation to that question, then, when you do the analysis in psychology of the meta-analysis in psychology, and the fixed effects models, were there good reasons for that not to correct error?
No, but typically they don't even mention it at all. They don't mention it at all. I don't think none of the ones that use fixed effects model mentioned. The question was, were there good reasons why they didn't correct for measurement error in the fixed effects meta-analysis? And no, they completely ignored the question. If you're still doubtful about some of the statements I've made, read those references, and I think they will